Hello. Basically, I will be explaining the Unibi amplifier and showing some simulations of the Unibi amplifier. In this figure, I have the basic Unibi amplifier. Basically, the Unibi amplifier is a very old amplifier that is a junction of a NPN transistor and a NJ-FET transistor. Then the NJ-FET transistor serves as an input tube to the Unibi to the NPN transistor in order to increase its input impedance. Basically, it turns its gate to drain potential, no, gate to source potential into a current based on its transcontents, and bipolar transistor will amplify its current through its beta. And this current over here will be this current, which called IB, which will be IB multiplied multiplied by beta. This amplifier, of course, suffers a lot of problems, but it was one of the first uh, mixed amplifiers that was used, because in those old days, basically the first amplifiers that were used were just bipolar amplifiers, and one of its largest problems it's its input impedance. And in this case, we basically are creating an infinite input impedance through the JFET. Okay, this is the equivalent small signal model of the amplifier. Basically, this is the gate resistance of J1. I wrote it wrong, it's not RB, it's RG. This is the common source capacitance of J1. Basically, this is a parasitic capacitance that will make a zero, a very high frequency zero in a frequency response plane. And this is called the gate resistance of the bipolars, seen in AC. This is the gate capacitance to ground, and this is the current source. This is the output impedance of the J1. This will cause some undesirable effects on the game, so this resistance over here will cause some distortions. Next, we have the parasitic capacitance between the connection of the source of the JFET and the collector of the NPN. And this current over here will be amplified by its beta over here and will pass to over here, causing a gain of V out equals to gain versus multiplied by GM J1 J1 multiplied by beta. Okay, now doing some simulations in ltspice. I actually created some basically some custom models from JFETs and for NPN, more to replicate in an IC process. So basically in this simulation, what I'm actually doing is that I'm actually sweeping the gate voltage. So by running a simulation, you can see the V out variation. I actually did so the gain is actually very low. The gain of the output stage In order so it's easier to check the variation and the amplification of the current. So I will see that the input impedance is almost non-existence. In this area over there is you should not care about that area over there because is when the diode is conducting, which almost never happens. Actually, in order to do not see this, I will check this to 0. So we don't see those undesirable effects. So here we have right there. And we can see that there is a gate current, but is almost non-existent. This is very important, so it means that the impedance, the input impedance is almost infinite. Now we check the current of the transistor. So this is the drain current of the JFET. And now we check the current of the bipolar. So you can check that in this area the current is being amplified. This is areas when the basically the NPN saturates and there is no more gain. It saturates because this voltage over here is almost is too low and you cannot push many more current. Now you can basically see that, so it's pushing so much current, so the voltage over here is basically the current that the NPN is pushing. Is basically VDD minus the current the NPN is pushing multiplied by the resistance. So in order to check in an AC analysis, so we can check it to an AC analysis to a decade. So points per decade we want 100, starting frequency we want 1, and frequency I want 10 gigas. I turn this, so I want to put the DC, I wanted to put the DC point and minus 1.5 volts, so I check this to a AC. DC minus, I want to put like 1.5 DC value, 1.5, I want to sample it to that, I want 1, and this is, theoretically this will simulate, so this is the gain that we are actually seeing. If you actually increase this, the gain will actually increase too, as is expected. Oh, it didn't actually increase because the DC point changed a lot. So we need to basically see a simulation in order to see where the DC point was. But if I do this, it probably increases. Yes, because it doesn't change the DC point too much. Now, the frequency response is basically the capacitance that we saw in the small signal analysis. Here we have a 0. Probably the 0 is this 0 caused by this capacitance. And then we have the drop roll-off of the phase margin. This is a very undesirable effect, but if we had actually capacitive load to the system, the frequency response will be very different. So I had some very quickly over here, just to, I mean, a good load. I mean, I will say 10 pico. It's a decent load. I will change this again. No, I would left this like this, and like this we have a more decent frequency response. So the 0 basically disappeared. So this is a more real AC response. You actually have a bandwidth of close to 100 megahertz, which for the power it consumes is very bad actually. It's actually consuming a lot of current. Again, by checking this, but it will it will reduce a little bit of the frequency. So if you want to amplify actually an AC signal, so I will check diff 1 mega. So I will write here 1 amplitude. I will put like 0.10, and I will get the frequency of 1 mega, just so we check distortion mega there, and we'll change this to transient signal. So start then. I have 1 mega, so I want 5 views, and maximum time step I will want 100 pico. Wait, stop time must be positive. Stop time. Oh, okay. Forgot. So I want 5 view right there, and I will run a simple AC, simple simulation. So basically, this is the input signal, and this is the output signal. Right there, we don't see a lot of distortion actually on the signal. I will require to do a Fourier analysis, which I don't really recall how to do. As yes, it's right there. 50. And I will check. I think it's this signal over here. By doing this, we can do the spectre. So you can see that there is not a lot of distortion on this signal. But if I've increased this too much, like to 3, this will start see some clipping on the signal. Actually, not so much, but actually the signal must have an higher distortion. So if I do this, I start to see that the second harmonic is start to appearing, the third harmonic too, and if I continue to increase this to more, like to 5, which now the signal will really change. We start to see some clipping over here. Not too much, but you can actually see it. If we check the frequency response of the signal, no, the FFT of the signal, we will check that this harmonic is start to climbing more and more. And if I to increase a little bit more to 7, the signal will clip, because the maximum is like this voltage over here. And yes, this is the clipping of the signal. Now, one of the largest problems of these amplifiers is because the gain and DC point actually change a lot with temperature, since it doesn't actually have a feedback loop. It needs a feedback loop in order to define this DC voltage, and the gain is almost always open. The gain is always open loop. It's difficult to fix the gain here to a certain voltage. This is the most important problems of these all the amplifier circuits. So if I do this, I now have a very high second harmonic and third harmonics and so on. If I keep increasing, I mean, the signal will keep becoming more like a square wave. So right here, this is completely distorted. If I do the view and FFT and I check it, I I get a really bad Fourier signal. But yes, that is all. Hope you enjoyed.